So now here this is our member again. We have direction 2 because this is in the principal y dash direction, so we have to select direction 2. But here the value is 25, but it is positive or negative? It should be negative because it's going upward, and sorry, it's positive. If it is downward, so it will be negative. So the force is upward, so it is positive. Apply, and can you see the force is correct? Here, the second step is member number 4. So, is there anything different? Same thing. This is perpendicular to the member, so direction 2. The force is 25. And apply. Okay. So, this is the forces we have applied to this frame. And now everything is ready. So, what is the next step after we assign or apply the load? The final step is to solve. So linear static, this example number 2, then apply, solve. So no problem. Close. Results. Open result file. Open. Okay. So now, if you want to show the deformed shape, this is a deformed shape. Okay. We can hide the forces if we want. Attribute display. So this is the deformed shape. If we want to show the shear force diagram, this is the shear force diagram, but we just need to make it undeformed. So this is undeformed shape. So this is the shear force diagram. Okay. If we want to show the bending moment diagram, so this is the bending moment diagram. Okay. As you can see, the parabola is inverted because the force is applied upward. If we want to show the axial forces on the frame, this is the axial forces. So this is how the axial force are. If we want to show the results on the contour, so we can show displacement or reaction or force. If we want to show the shear force or axial as a contour, so we can show the sections first, solid, apply. So this is the axial forces. How much is the axial force? What is the largest one? So under infinity display, I will show the member number. So this is the member number, this number 1, 2, 3, 4. So the maximum, all of them under tension. The maximum tension is at the top here, which is 139.4 kilonewton in member number 1. So member number 1 will be under maximum tension. If we want to show a different results type, we can show the displacement. So this is displacement. What is the displacement we need to show? We can show dx and dy because this frame is under 2D or is a 2D frame, so we cannot show dz, so we can show only dx and dy. Okay, the last thing we can show here is the linear loop case. Sorry, we don't have linear loop case combination. So we have to we can do animation. So we can, this is, we only have single case, so we can apply this. So this is the animation, but we can choose the animation for the diagram, and so you can choose the results. So this is the animation of the deformation. So this is how the frame will be will animate or will move under the load we apply. Okay. So do you know how to create the animation again? So we can select any case like result settings. Let's say diagram, bending moment, apply. But we can use diagram. So this is the diagram of moment, and this is how the moment animate. If we want to make it clearer, we can make it line and apply results. Maybe you can change the color of the moment to be different from the the beam element itself. So now we can, under results, create animation and run. So this is how the frame animate and how the moment move with the animation. Okay. Do you have any question for this example? No question. So now if we go back to our example, I will do example 3 and then have a small rest and then continue. Okay. This is a simple example, but it has two cases. So it is like a cantilever or like a cantilever deep beam, and we need to do it twice using two different type of models. Okay. So firstly, we will do it as example 1 and 2. So we can do it as 2D elements, 2D beam elements. And then after this, we will try to make it as a plane stress element. Okay. So do you have any question about this one? Okay. So now you share, go back to the software. So we will have to open a new file. The stress megapascal, forces kilonewton, temperature is Celsius, no change in the top part. So now, before I start drawing or modeling, just some to make it simple for us to do it. So here, like example number 3, we have, this is our member. So this is 8 meter and this is 1 meter. Okay, and we have applied load 10 kilonewton. We have E equal to 24.6 gigapascal, and we have nu is the Poisson ratio 0.2. We have rho, the density is 2640 kilogram per meter, cubic meter, and Ct is the thickness of the element, which is 0.1 meter. Okay, so if you cut here and have a look, so this will be our cross section. It is 0.1 meter times 1 meter. Okay, so this is some explanation. Also for the units, for rho, no problem because we have kilogram in mass, meter is the length. Nu, no problem because it is unitless. 0.1 meter is okay. But here, we are not using gigapascal. How to convert from gigapascals to megapascals? From giga to mega, we have to multiply by 10 to the power 3. So now E will be 24.6 10 to the power 3 megapascal, just to help us to when we enter the data to the software. What is needed as well? To draw this, we need to have, this will be our beam element. This will be x-axis and this will be y-axis. How many nodes we have to draw? Node 1, node 2. What is the dimension, the coordinates? If this origin, so 0 and 0. If this second point, so it will be 8 and 0. Okay, so this is our details of the problem. So now we go back to the software. So firstly, I will start creating a node. In this part, we will start with 2D beam element. So create node. Node number 1 is 0. Node number 2 is 8 and 0. So this is the two nodes. And now we have to create a member. We have only one member. So property number 1 and beam 2. So connect them with a member. So now the type of member is beam element and under property number 1. So now we have modeled the member or draw the member. The next step is to assign the supports. We have node restraint. How many node restraints we have? We have only one here, so select the node. What is the type of restraint or support? Fix, so click fix, apply. So the support now is fixed support. What is next step? The next step is to define the material properties or the section property. So under property, beam, if we want to change the name, so make it like frame or beam 1. Then here, the material is not steel. It is not a known material, but the problem gave us some details. So what is the details given? The modulus of elasticity given to us as 4.6 times 10 to the power 3. So that's it. For the Poisson ratio, it is 0.2. For the density, it is 2640 kilogram per cubic meter. No other data was given. What else we need to enter? The geometry. Or we don't have this section area, or we don't need to do this. But if we enter the geometry, this will fix the problem. So the geometry, we can go to edit. What is the type of geometry we have? It is a rectangular section. So click this one. B is the width, D is the depth. So B is 0.1 meter. The depth is 1 meter. So now we have the member is rectangular, and we have a look on the cross section, and it is okay. Then close. So now if we have a look on the infinity display, so what we have, remember, is now ready. Okay, so what is the next step? The next step is to add the load under attribute node, load or force. Select the node, this node. What is the load we have? We have 10 kilonewton in y direction because it is vertical, but it is downward, so negative. So apply. So we have 10 kilonewton here. If we have a look on the attribute display, attribute point force, show the value, apply. So it is a node, force, show the value, apply. So now we have shown the value, and now everything is ready to run. But before we run, we will learn here a new like software order, or a new thing we need to do, which is subdivision. So to get the best result from the software, we have to subdivide the element to small elements. So when we make more subdivision, we get more results. We got more accurate result. So how to subdivide? If we go to tools, under tools, you can see a lot of uh, a lot of things we can do under this. So this anything you can copy, move, extrude, subdivide, cut, all of this can be found under this tab. So here we need subdivide. So subdivide is there. And if we look here, the subdivision has three direction, A and B and C. If we are doing beam element, like what we are doing, so we need only A. If we are doing a plate element, so we need A and B. If we do a brick element, so we need A and B and C. Okay, so that's why this doesn't matter for us. So it will be 1. 1 doesn't matter. But if we keep it 1, so the member will not be divide. If we make it 2 like this, let's see. If we select the member and click 2, so this subdivide the member to 2. If we want to make more, so let's say 10, so it will subdivide the member to 10, and so on. So if you want to more accurate results, you can subdivide more. Let's say we will subdivide this to 20 parts. So apply. So this now is on 20 parts. So how much is the length of each part? The whole beam is 8 meter. So each part will be 8 meter by 20. So it will be about 400 millimeter. So each part of this is to 400 millimeter. If you wanted to do more, you can select more number of subdivisions. Okay. So now we have this just to make it more accurate. And now we are ready to run. So run linear static. Example number 3, part 1. And then solve. We have no errors. Then open the result file. Open. If we want to show the deformed shape firstly, so we have the deformed shape. So this is the deformed shape. If we want to show the bending moment and shear, so this is the shear. If we want to show the bending moment diagram, this is the bending moment diagram. Okay. If we want to show the contour, so we can choose the contour, the shear force diagram as a contour, or the displacement as a contour. What is displacement is here, dy, so apply. So this is the displacement. If we want to create animation for this, so create animation. So this is how the beam deflect. Okay. Now, what is the maximum deflection? The maximum deflection is negative 8.32 times 10 to the power negative 3 in meter. So this means that the maximum displacement is negative 8.3 at the end here. If we stop the animation, okay, if we look at the displacement, so the maximum displacement is negative 8.32. Okay. In the example, if we go back to the example, or the problem, the head of the problem. So what is required here? If you look here, what is required? It's required to compare the result dy sigma xx tau xy. So now this is dy. So you can take a screenshot of this to compare with the second part of the example. Now the result we need to show again is the stress. So contour stresses. What stress we need to show? Sigma xx. So what is sigma xx? Sigma xx is the bending about plane 1. So apply sigma xx is the moment, the bending moment, stress 2. So again, result settings, contour stress bending plane 2. So the bending plane 2 is equivalent to sigma xx in our problem requirement. Okay, if you can have a look on the stresses here, the stresses here as expected. On the top fibers, we have the maximum tension, tensile stress or tension, the pink, which is 4.8 MPa. At the bottom, the maximum compression, which is negative 4.8. Okay, and the stresses are decreasing until going to the minimum, which is negative 7.5 times 10 to the power negative 2, negative 1. Okay, because it is a cantilever, so the maximum stresses should be at the supports like this. Okay, if we want to lastly show the final requirement of the result, the shear stresses tau xx, tau xy, so it is transverse shear plane 2. So this is the shear or the transverse shear plane 2. Okay, so because we are doing the bending moment about plane 2, so sigma xx and tau xy are the shear and moment stresses about plane 2. Okay, here the maximum stress at the middle, as you know, the maximum shear stresses will be at the centroid. So that's why the maximum shear stresses are 1.5 times 10 to the power negative 10 in the middle, which is logic. Okay, so now we have finished the first part of example 3, which is modeling this problem using a 2D beam element. Okay, the second part is doing this problem again. So new MBA kilonewton Celsius, but it is required this time to model it as a 2D plane stress element. Okay, so now if we go back to the SharePoint here, okay, so now how to model it as 2D plane stress element. Okay, the plane stress element, as if we remember the from the previous lecture, it can be quadrilateral element. So it need to be an area, cannot be a line element. So what we need to do is converting this element to a quadrilateral area so we can draw it. So what we know is this is 8 meter, this is 1 meter, and this is fixed. So what I will do is to draw it on the software, I will make 4 points. This node number 1, node number 2, node number 3, node number 4, And to draw them on the software, we will assume this as the origin, 0 and 0. So this will be our y-axis, and this will be our x-axis. So the coordinates will be 0 and 0, 8 and 0, 8 and 1, and 0 and 1. So this four nodes has known coordinates now, and now we can go back to our software and to do the modeling. Okay, so now I will start creating node. Node number 1 is 0. Node number 2, 8 and 0. Node number 3, 8 and 1. Node number 4 is 0 and 1. So now we have the four nodes. And now we can create the 2D stress, plane stress element. So now under create element, but it is not a beam. It will be a quadrilateral 4. We can draw using quadrilateral 4 or quadrilateral 8, but to make it easier when we draw first, we can do it as quadrilateral 4. So now connect the member, start with node 1, node 2, node 3, node 4. So now the plate is drawn. So this is how to draw the plate element or the 2D plane strain or plane stress element. You need to have four nodes, otherwise you cannot draw. But for beam element, we need only two nodes. Okay, so this is our first step. Our second step is to assign the supports. Here the supports, we have node restraint. But the support here, not only one node, because all this side is fixed, so we have two nodes. So select these two nodes and fix, apply. So now this plate is fixed at the left. The next step, as we know, is the probability to define the material probability. So under plate, because this is a plate element, not a beam element. So this we can rename this to make it 2D plane stress. So I change the name to 2D plane stress and okay. Okay. If we want to change the color, make it orange, let's say. So first of all, what is the type of element here? We have 2D plane, 2D plane strain, 2D plane stress, axisymmetric, plate shell, shear, and so on. So we have to make it 2D plane stress because this was the requirement of the example, and this is the best type to use in this example. Okay, now the material need to be defined. What is the modulus of this material? 24.6 times 10 to the power 3. The Poisson ratio is 0.2. The density is 2640, and we don't have any other geometry, any other property. The next step is to geometry. The membrane thickness. What is the membrane thickness? The membrane thickness is the thickness of this place, which is given as 0.1 meter. The element, if we want to make it quadrilateral 8, we can change the element from here, but we will keep it as quadrat 4. So close, and now if we view, if we want to change, just to refresh the view. So this is the plate view, solid. Now change. So now we have applied the material properties and the section properties. The last thing is to add the loads. This loads is applied as a point load or the node force. So force node, this force was applied on the top, so I will pick the top point here, and then -10 is okay, similar to the previous part of the example, and apply. So now we have a force applied at the top. If you want to show the value, so view, infinity display, attribute display for the node, force, show the value, apply. So as you can see, the force is negative 10 kilonewton. Now, similar to the previous part of the example, we need to create subdivision. You cannot solve any plate on the finite element modeling without subdivision. That's why in beam element, the subdivision will not affect the accuracy much. So we can neglect it sometimes, but for the plate, we cannot do the modeling or the solve or the like or the analysis without subdivision. So now under tools, subdivide. Here's the subdivision as I mentioned before. The subdivision is A and B for plate. If you select the plate, as you can see, this is the subdivision in direction A and the B direction in the vertical direction. So can we make it 20 in A and 20 in B? This will not be good because as we know before, the best ratio between the elements dimension need to be less than 3. So it can the best is 1 to 1. So if we want to make it 1 to 1, so we have 8 meter. If we divide 8 meter by 40, it will be 200. And if we divide 1 meter by 5, it will be 200. So if I subdivide 40 in A and 5 in B, apply. So as you can see, it is rectangular. So it is square. Each square is 200 by 200. Okay. If you want to make it less subdivision, you can do it as well. But I choose to make it square 200 by 200. Okay. Now we are ready to solve linear static. So example 3 part 2 to run the model. So what we have now, solve. We have no errors. So result, open result file, open. If we want to show the deformation first, deformed shape. This is the deformed shape as expected. If we want to show the results, what result we have shown? We have displacement dy in the previous part of the example. So this is dy. So here, what is the maximum deformation? Negative 8.418. Okay. If you go back to the first part, it was about 8.39. So it is very close. So no problem, not much difference, but this is more accurate. Here also, if you want to show the stresses, here for the stresses, we need to show sigma xx. So this is clear for us, sigma xx, apply. So this is the stresses. As you can see here, the stress is 4.9 at the top, negative 4.9 at the bottom. If you want to show as we showed last the previous example, so it was like this. So the maximum stress is at the top because it is under tension, positive 4.9, at the bottom negative 4.9. If we want to show tau xy, which is under stresses xy here, apply. Okay, so these are the stresses. As you can see, the shear stresses here is the contour looks different, but we are looking on the values. If we check the value, the maximum value is in the green here, very close to the center as well, which is negative 1.13 times 10 to the power negative 1 or negative 1.34. So it is going up. So the maximum negative is negative 0.197 times 10 to the power negative 1, which is at point 164, node at plate 162, node 4. If we want to show the node number, view, infinity display, to know exactly where is the maximum node number. It will be hard to know, but as you can see here, the numbering, node 4. So the maximum shear at node 4 here, as you can see, can you see it? This one. So the maximum shear at the support at the top and the maximum shear here at the bottom. So if when we compare the beam element to the plate element or the plane stress element, the results are close in the deformation, but not very close in the shear stress because of the plate the plane stress element model better this deep beam because this is a deep beam. So the 2D beam element may be good in modeling the to get the deformations, but not very good to get the stresses. This is the idea of this comparison. Is to know which element is better, the beam element or the 2D plane stress element. Okay, if we want to show a different result like the contour of the displacement dy again. So here, as you can see, where is the maximum displacement? The maximum displacement is at node 3, negative 0.84. So this node 3 has a very far right. If we want to run the animation, create animation. So this is the animation. Because here is fixed, the left part is fixed, so it can't move. Also, if we want to show a different result like the node reaction, what is the reaction we have? We have fx, fy, and mx, my. So if we show fy, okay. So the maximum reaction are at the support as expected. The maximum reaction is at point 85, which is this node. The maximum reaction is negative 0.219 kilonewton. Okay, so negative 2.1 because the reaction here at the support should be the summation of the whole reactions. That's why it is not 10. If you sum the reaction at these four nodes, so you will find them the summation is 10 kilonewton. Okay. If we want to show a different result, like stresses again, sigma xx, and create the contour animation. So this is how the stresses change with time or with applying the load. So this is the animation for this file. Okay, if you want to stop. Do you have any question for this example? Okay, we'll just have a rest for 5 minutes and come back, or 5 to 8 minutes. Okay. Okay, thank you. Okay, so again for problem number 4, we have a plate element under tension. The width is W, 200 millimeter. The slot or the hole length is 2h, which is equivalent to 100 millimeter. The width of the hole is R, which is, sorry, it will be 2R, which is R, 1R is 20 millimeter. The thickness of this plate is 5 millimeter. This strip is under tension, but this strip is symmetric about x-axis, so we'll take bottom half, and about y-axis, so we will take the left half. So we will only take a quarter of this problem. So this is the problem we will be working on. Okay, what we need to calculate is the stress concentration factor or the stress on this plate. Okay, if we look to the next slide, So this slide is a hint, is how the quarter will be modeled. So this is the quarter we have. So the quarter dimension is 150 in this direction and is 100 in this direction, because we already have W is 200, so we take only 100. Okay, and here we take only 300 of this. So because it is not given, but it will be taken as 300. So the half is 150. So it will be 150 times 100. And here, the slot, we have the radius of this circle quarter is 20 millimeter. And we have the remaining of the slot is this part, which is 30 millimeter. So this is a quarter we are modeling. And now I will share my screen. So example number 4. So if we want to draw this on the software, so we will have this part. Okay. So we will divide this bar to, we have node. Okay. So we have this part. Okay. So now we have region 1, region 2, region 3, region 4. The dimension is 80, 70. The dimension here is 70, 30. So the total here is 100. The total here is 150. This part is 20 millimeter, 50 millimeter. This part is 30 millimeter. Okay. So how to draw this on the software? If we follow same method as we have done before, so we can draw it with the coordinates. So we have, if we consider this 0, so we have, this is our y-axis. You can select what is the easiest way to draw it. So this is x-axis. So if we number this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have 12 members, 12 nodes like this. If we want to do the coordinates for them, so we have 0 and 0, 0 and 80, 80 and 0, sorry. And here we have 150 and 0. Here we have 150 and 50. Here we have 0 and 70. Here we have 80 and 70. Here we have, if this 20, so this will be 50. So 50 plus 80 will be 130 and 70. 0.8 will be 150 and 70. Here is 0 and 100. Here is 80 and 100. Here is same to this one, 130 and 100. Here is 150 and 100. So this is all the dimension or all the coordinates of this blades. Okay, so now we'll share the software. Can start drawing. So we'll again open a new file. Megapascal, kilonewton, Celsius. The unit here, we can use millimeter as it is, the dimension is given as millimeter. So to make it easier for us, we can make it millimeter here. Okay. So now if we start creating the nodes, 0 and 0, the other one was 80 and 0, the next one. The third one was 150 and 0. The third one is 150 and 0. Apply. We'll start again. So create node. Node number 1, 0 and 0. Node number 2 is 80 and 0. Node number 3 is 150 and 0. Okay. Node number 4 is 150 and 50. Node number 6, node number 5 was 0 and 70. Node number 8, 80 and 70. And the next one is 130 and 70. Okay. And 150 and then 0 and 100, then 80 and 100, then 130 and 100, then 150 and 100. Okay, so this is all the nodes we have, as you can see. So if we want to draw the blade, so create blade element quad 4 because we are 2D plane stress. So connect this one with this one with this one and this one. So this is the first plate. This one with this one, this one, this one, this region number 2. This one, this one. Sorry, we have missed a node here. So create node. It was 150 and 70. Apply. So again create element, quad 8. So from here to here to here to here, this plate number 4, and this is the last one. Okay, so uh, we have already draw this part. Okay, we just need to cut a part from this plate. So under tools, you will find cut beams and blade, or grade beams and blade. So grade blades, if you can see, we have some grade options. If we try to select this one is the one we need. If we try this one here, okay. So this one, because the ratio is 0.5, so it is not correct. So how much is the ratio we need to cut from this edge? If you can see, we need to cut, if we go back to the share bar, to the problem itself, how much is the cut from the whole plate? This is 70 and this is 70 and this is 20. So we need to cut 20 by 70, which is 0.285%. So if we select again the two edges, because we need to cut a quarter of circle from here, and select this type of cut, this is the one we need, and we make the ratio to 857 and then apply. So as you can see, it is cut. Okay, so now we have start drawing this part, and there is a lot of option to draw. You can select whatever the option to draw it. And I want to remind you of something, that if we go to screen 3, this is a tutorial, same tutorial. This is the solution of this part. If you can have a look on it, it's already shared this with you, and it is only also on the website, the Learn Online website. Okay, so this is the plates, and you can follow step by step. So maybe it is a different way to draw, but at the end you will reach same thing. Okay, so this is the plates we have done, and using the cutting edge. So now we go to same step. Okay, do you have any problem until now? So the next step is to subdivide. If you can see, the subdivision is a hint given here. Subdivide region 2 to 2 by 3, division region 1 3 by 3, division 3 3 by 4, division 4 region 4 subdivide 2 by 4. So if we go to the software again, so now for this region 1, ask it to subdivide. So before selection, I will go to tools, subdivide. So how much? This is A and B. So the first is X, which is the horizontal, and the vertical is B, which is, no, sorry, this one is 3 by 3. So we need to subdivide this 3 by 3, so it doesn't matter which one is which. So if we divide A3 and B3 and apply, so this means that we subdivide 3 in X, or 3 in A direction, 3 in Y direction. Okay, for this one, what do you think? It is given as 2 by 3. So the subdivision need to match if these two plates are adjacent like this, so we need to match the subdivision. So we need to make it at least 3 in A, so it can't be less than 3. And in B, it will be 2 because the distance is not big, so we will make it 3 by 2. As you can see, the subdivision is matching in this area. So we have 3, 3, so it's match. This area as well, it will be 2 by 4. So which 2 and 2 4? Which 4? 2 will be B because need to match with the the one next to it, which is 2. So we will make it 4 by 2 like this. So this will be match in this direction. They are match. If this 2, so this 2 as well. But here why it is 4? Because here we have a gap, a hole. So we need to make small meshes here. As you can see, the line here is small and the line here is long. So is this short and this long? So we need to have like ingredient or transition mesh. That's why we was asked to subdivide this to 3 by 4. Which direction will be 3? Which direction will be 4? B will be 3 to match with the next one. So this will be 3. And A will be 4 to match with the top one. So if we apply, so now it works. Here, again, it will be also 4 by 3 to match. Apply. Okay. So now we have subdivide all the or meshing. It's called subdivide or meshing. So we have subdivide the problem. Okay. So what is next? The next step after subdivision is to make this our quad 8. Quad 8, if we want to make this quad 8, we can make it while we are subdividing, or what we can do is select all of them and using, if you forget to subdivide, when you subdivide, you can subdivide, make this quad 8, but we make it 1, so nothing will be subdivided. So if you have a look now, you can see that each element, look at this element has 8 nodes now, so it is quadrilateral 8. So you can convert from quadrilateral 4 to 8 easily by tools subdivision. Select the member or the blade and make it quad 8 instead of quad 4. Okay. So now we have subdivided all the blades to quad 8 and all the meshing are matched. Okay, but we still have some problems. What is the problems we will face here? We have some problems at the radius or the circle or the quarter of circle here. So after subdivision, we will choose the global coordinate system. And under global coordinate system, we will go to coordinate system and then make a new coordinate and make it USC, new Universal Coordinate System. And under select, under system, select cylinder. So we will select cylindrical. And then XY, select XY, it's already selected. And for the origin point, select node, this node. So where is the origin? Can you see the origin here? So we click this one and select this node, then apply. So now using this step, we are trying to justify the nodes, the coordinate system of this nodes to be related to the center of the circle here at the origin node here. Okay, just to make sure that this edge is correct or the dimensions are accurate. Okay, so the next step, Okay, to make sure that we have done correctly this step, so we will toggle the node selection and go to okay and click shift, and we will hold the node, but we just need to close the blade. If you can see here, can you see the X? The dimension is not very accurate. Can you see? Some of them are not 20. So this means that the circularization of this, they are not accurate. So what we will do is choose select by region, go to select by region. So we will go to select by region, and then under theta, we have theta. So select wrap. So click in the end nodes of the slot radius. So we will click on the node, as you can see, and then nudge one. Click on the nudge axis one. Okay. So this is add and this minus. So we click nudge axis one and then apply. Okay. And then under tools, after we select, okay, after we select all of them, under tools, move, where is move? And by to absolute. And under this, what coordinates we have? USC cylindrical, and then under fix R, so we need to fix the value of R. So we need to enter 20 to make all of them 20, then apply, and then close. So if we have a look again using shift, so what you can see, all of the first coordinate, which is the radial coordinates, is 20. Okay, so now we are sure that this is a circular or a curve related to the center, and this is a problem with the software or any software. So this is how to fix this problem. The next problem is the meshing. We may have some problem in the meshing or any duplicates or something like this. So we can have a step of mesh cleaning. The mesh cleaning will be using tools as well. Clean mesh. Can you see clean mesh? Where is clean mesh? The last one under clean mesh. So we have to keep the default settings and just all check, like apply for all, and then click apply. Yes. So this is what happened. So the two nodes have been deleted because they were duplicated, and now we close. So the mesh is cleaned now, and the next step is to apply the loads. What is the loads we have here? We have only, if we go back to the first drawing, the problem definition. So we have only a stress at this part. So we have a stresses in this part to the left here. So this called edge stress. So we have edge stress on the left side of the blade. So we'll go back. So now we need to apply this load here. So we can apply the load by selecting node by node, but it's not good. So what I will do is using attributes. plate, edge loads, because this is edge load, and using pressure, so pressure. So this is how to apply. We can select the nodes here or using global. This is another way to select. So global and using the Cartesian global axis. So what we will do is click this node on the top, just to toggle this one here. So click the node on the top. Okay, again, attributes, plate, edge load, pressure, and then from select by region. We need to select, so select by region under the Cartesian node. So we now under the Cartesian or coordinates. So we will select the top node here and the bottom node here. Can you see? Now the edge is highlighted or dotted. This means that we already have selected this edge. Now we can select the value. The value is not given to us, so we can select it or assume it as 100 as the example. So we will select it as example 100 megapascal. So we click apply. Now we have applied 100 megapascal of stress to the left. If we want to show the value, attribute display, plate, edge load pressure, show value, apply. So as you can see, how much is the value? 100 MPa. So what is the next step? The next step is the freedom condition or the supports. If we just apply the load here, so will happen? This plate will just move or will be unstable because nothing to support it. So what we will do is using the symmetric condition. If we go back to the symmetric condition, so we will share with you something. So this was the original problem, right? So this is x-axis, this is y-axis. So this was the part we deal with, okay? Why we said we deal with this part? Because we said this is a symmetric axis, so we take this part. This also is a symmetric axis, so we take this part. So we should benefit from this symmetry. What is the benefit of this symmetry? So if we take this part out, so this is what we have. So the symmetric give us boundary condition or restraint. So these restraints are from the boundary condition. So if we say this line is line of symmetry and this line of symmetry, so at this line we will have some restraints or some boundary condition due to symmetry. Okay. Do you know what is the type of symmetry? What is the restraint we got from this boundary condition, from this symmetry? Do you have any idea? So if this line of symmetry, I will start with the y-axis. So this line, because it is symmetry about y, so we don't have any deformation in X. So X is not allowed, but Y is allowed. So I will draw the not allowed deformation with sky blue and the allowed with a pink. Okay. So because of this line of symmetry, so X is not allowed, but Y is allowed. So this line can move vertically, but cannot move horizontally. Okay. Similarly, for this line of axis, for this line of symmetry, because X is line of symmetry, so these points cannot move in Y. So Y is not allowed. But for X is allowed in this line, on this line. Okay. So X is allowed. So this is how we benefit from symmetry. So what is the benefit from symmetry? The benefit from symmetry is we can deal with only a quarter of the plate, and also we have two not allowed deformation, which make restraints. Otherwise, the plate will keep moving forever. So we have two not allowed displacement and two allowed displacement due to symmetry. So if we go back to our problem again to apply this restraint to the problem. Okay, so this line will be allowed to move in Y, but not allowed to move in X. This line allowed to move in X, but not allowed to move in Y. So what I will do is, okay, firstly, under global, because this is a plate, 2D plate, we can also assign as a freedom case. So under the freedom, as you can see, under global, load and the freedom cases, you can choose that your problem is only in 2D plane. So you don't have to assign Z. So if we apply 2D plan, so we have freedom load case, or we can change its name to make it 2D plane problem, just to make easier for us to notice. So under 2D freedom cases, 2D plane problem and 2D plan, and okay. So now we don't have to worry about Z. So what is next? Under attributes, we will use under attributes, nodes, restraint. We can again select by region, and under Cartesian nodes, select this node and this node and click apply. So now you select these nodes, and now what is the free? Are these nodes are free, or they are not allowed to move in X as we mentioned, but allowed to move in Y? Okay, so apply. Or another thing, we can use Y symmetry. As you can see here, just to go back again. So after selection, attributes, nodes, restraint. So these nodes are on the Y symmetry or axis symmetry, X symmetry. This under Y symmetry. So as we mentioned, this will prevent the movement in X and allow the movement in Y and prevent all the rotation. And we don't worry about Z. So that's what we need only. This is the main thing. Prevent the movement in X, allow in Y. This is the things I was explaining to you before. So just go back again. We don't need the selection We just firstly, because we have a selection from a previous problem, clear all selections, and then attributes, nodes, restraints, select, just to make sure that you have only the selection you want. So by region, and then select the first node, select the last node. So he will select the nodes. You can see it is purple now, and use Y symmetry. So apply. So now we apply the restraint here because of the symmetry. Because if you model all the problems, so it will work like this. So because of we take only a part, so we need to follow this procedure. Now clear selection, and again attributes, nodes, restraint. This one is X symmetry or Y symmetry. This is X symmetry, X symmetry. So X symmetry. So we select X symmetry and apply, but we have to select the nodes first to under selection by region. So select the first node here, the last node here, and then apply. So the selection is ready. Now apply the X symmetry condition. So now everything is okay. So now we have all the we have all uh, the meshing ready, all the supports ready. What is the next step? The next step is just to define the material property. So the property under plate, is it plate or 2D plane stress? 2D plane stress. If we want to change the color, we can make it yellow this time. You cannot solve without entering a material property. Otherwise, the software will not understand the type of the plate. Okay, so click on the material. We need to change the material. So we will select, this is in the details of the problem. So we will click on mill MDBK 5G carbon steel. So this plate is from carbon steel, and under carbon steel, we will use AISI 1025 cold rolled sheet. So this is a cold rolled sheet, and then okay. So this is the material, and this is given in the problem details. And then under geometry, we need to give a thickness. The thickness was given as 5 millimeter. So apply. So now we have apply the material property to the blade. So if we want to see the blades, this is the blade shape. So we change it to yellow. Maybe we can, if you want to change it to the different color, doesn't matter. So now the model is ready to run. So we have finalized everything. All the everything is okay. Now under solve, linear static analysis. So this will be under example number 4. So this number 4, and then save, then solve. Okay, no problem, no errors. So that's good. So under result, open result file, and this is the result file. Firstly, if we want to show the displacement or the deformation, this is the deformation or the deformed shape. Okay. If we want to show the stress concentration, so we will close again the deformed shape, and results, result settings, contour, stresses. We can show XX. This is the XX stress. So this is stress about XX. This is YY. This is the shear tau XY. Okay. If we want to see the stress distribution on the combined, the on the like the the requirement of the stress concentration, we have to under contour stress, we will select the combined global axis. So we have component 1, 1. This is the one we are looking at. So select stress, component 1, 1 under combined axis system, and see, this will be the results. Okay. So this is the stress concentration at this hole. As you can see, the maximum stresses in tension is 5.016 times 10 to the power 2. The maximum in compression is negative 5.99, which is almost 6. If you go back to the the original file or the original solution, I will share with you. If you can see, you can see that the results are very accurate. We have same results. So our solution was good. We don't have any problem. Okay. So the maximum here is 516. The maximum in compression is negative 5.9. So we got same results. Okay. So this is the things the the stress we need to do on the software. Well, this step is just a step of calculation to find the maximum principal stresses. Sorry, the maximum stress concentration. So, or the factor of stress concentration. If you go back to the original original problem, so we need to calculate the stress concentration factor. So after we finish the model, using the model result or the model output we find that the maximum principal stresses 1 is 5.16. If we go back again to the software, so again the maximum principal stresses 1 is 5.16 times 10 to the power 2. This is the maximum. So we are correct. Now if we go back to the calculation, so using the maximum principal stresses 5.16, we can compare and get the stress concentration factor. So sigma reference stress, this is equation we need to know for this example. The reference stress is sigma applied, which is 100 times W, the width of the height of the hole, divided by the width of the hole minus 2h. So again, I will share this with you to make it easier. So if we have this, this is our plate again. This will be our last thing to do today, and I know we have exceeded the time, but just to finish this problem. So this was given as this 2h was 100 millimeter. The stress here sigma was 100 MPa. R was given as 20 millimeter, so the width is 40 millimeter. The thickness of this blade is 5 millimeter. W, the total width of the blade was 200 millimeter. Okay, we get that the maximum principal stress on this area was 516 MPa. We will use this value from the software to find the stress concentration factor. To find the stress concentration factor, we need to find firstly the reference stress. The reference stress is sigma reference, which is equal to, this is the this is the stress at any point except for the hole. So this is sigma reference, and it will be sigma times W divided by W minus 2H. What is this? Sigma minus W is the stress over any part here. So the stress here is normally sigma times W over W. That's why it is sigma. But here, because we deleted part, so the stress here is a little bit concentrated. How can we find sigma reference here after we cut a hole? It will be sigma times W, the normal, but divided by the width minus the hole. So it will be 100 times 200 millimeter divided by 200 minus 100 millimeter. So sigma reference will be 200 megapascal. So the stress at any node at any points on this line, two lines, is sigma reference equal to 200 MPa. So now compare to the stress concentration, how much the load factor? If we now we have sigma principal is equal to 516 MPa. Sigma reference is equal to 200 MPa. So the concentration factor, stress concentration factor, K dash, is equal to sigma principal over sigma reference, which is equal to 516 over 200. So it will be 200.58. So the stress concentration factor is about 25.58. And this is the requirement of this problem. Okay. Do you have any problem with this? Do you have any question or any problem? Okay. If we go back to the software, if you want to show more results, create animation. This is how the stress happen, how the stress change with applying, how the the stresses on the blade change with applied edge pressure. Okay, and that's all for today. Hopefully you get what I have explained today, and if you have any question, just please send me on WeChat or on the or by email, and we can have a better explanation for what you need. Okay, I will stop recording now.